The problem statement from GATE Physics 2012 reads as follows. Identify the correct energy band diagram for silicon doped with arsenic. Here Cb, Vb, Ed and Ef are conduction band, valence band, impurity level and Fermi level respectively. We are shown four options, each of them containing a band diagram. This is a multiple choice question with only one correct option and we have to choose the right one. Now, note that the question says that this is a silicon semiconductor which has been doped with arsenic. So let's have a look at this section of periodic table. Silicon lies in here in group 14, right? So these are 4 valence electrons. On the other hand, if you in the group 15, if you see you see arsenic, here. Now arsenic has an extra electron, so they have 5 valence electrons. So when it bonds with silicon, it will have one extra electron that it can donate. Note the word it can. It doesn't necessarily has to, but it can. So it can donate, and thus a silicon, and thus the electron eventually. So you see this is arsenic, and this is the extra electron. Note that this is silicon. So every other silicon is bonded to silicon, and however when there is an arsenic, there is an extra electron floating. And what essentially has happened is that if you provided sufficient thermal energy, this electron will become free. How do we denote this in terms of energy band diagram? You see this is the arsenic level. This here we call it Ed. This level is Ec, the conduction band level, and this is Ev. Since arsenic is donating an electron and the silicon semiconductor becomes electron rich, we call such a semiconductor n-type silicon semiconductor, because silicon is the substrate here, right? So arsenic can donate an electron. Let's say it has donated an electron. So how do we show this? So we show this by this level. You see this level, where we have the black circles. This is the energy level of the electrons. These electrons are currently residing in this energy level. This energy level is very close to conduction band, which denotes that just due to some thermal energy, let's say some 100 Kelvin, if we give the temperature of 100 Kelvin, these electrons will jump to conduction band. And once they jump to conduction band, they're free to conduct the current. So this electron is loosely bound to arsenic. Just at some temperature, a low temperature like 100 Kelvin, this electron will become free, will jump from here to here. And this level between Ec and Ed, that depends on the donor level. That depends on the donor. So arsenic will have different Ec minus Ed as compared to phosphorus or nitrogen. But the common factor remains that Ed will be fairly close to Ec. So this means, so you see this is the mid band gap, the dotted line. So Ed will usually be very close to the conduction band. And since Fermi level, you see this Fermi level by shown this black dotted line here, the Fermi level we know statistically is the energy level at which the finding the probability of an electron is half. So at 0 Kelvin, all the electrons will be bounded with arsenic at 0 Kelvin. So hence this is the state that we see, all filled in Ed. All electrons are in Ed state, and conduction band is obviously empty at 0 Kelvin. And statistically, so Fermi level will lie at mid gap between the two. Hence Ef will lie somewhere between Ed and Ec in terms of n-type silicon. So we have determined that in terms of n-type silicon, in this case doped with arsenic, Ed, the dopant level, will lie somewhere above the mid gap level and close to conduction band, and the Fermi level will lie somewhere between the dopant level and the conduction band level. So now let's get back to our question and see which one of these band diagram matches. So remember, what we had determined something like this. So this was the conduction band level, this was the valence band level, and I'll denote Ed by blue color. So Ed, we noted that it was close to the conduction band. This was the Ed, and we also saw that EF was somewhere between conduction band and, so this was the diagram that we that we analyze. So our answer should resemble something like this. So let's go through the options one by one and see which one is correct. So we know that ED should be close, somewhere close to the conduction band. So ED is close to conduction band, yes, this is correct. ED is close to conduction band, yes, this is correct. Now ED is far from, this is very close to valence band, so this cannot be the answer. Similarly, ED is close to valence band, this cannot be the answer. So only one of these two options is correct. And we also know that EF should lie somewhere between ED and conduction band. Okay. So if you notice that in none of the options this is the case. So EF usually at since since nothing is given, we'll assume that it's room temperature, so at 300 Kelvin. So at 300 Kelvin, what should happen is that EF should lie somewhere between ED and conduction band, which is not the case in either of these cases. So neither this is correct, neither this is correct. So this is a peculiar question in which none of the options is correct. None of the options is correct. And actually, if you look at the answer key, this it says, the answer key says marks to all. So we have analyzed it correctly, right? So this is the energy band diagram that it will look. It doesn't match any of the options, but we solved it. That's what matters. Thank you for listening.